Hi, thanks for your time today. My name is Jeff Kleynen based in Japan, from Pacnet, on the services engineering team. And just want to talk a little bit about how backbone architecture is running over the subsea systems today, and some ideas of some better ideas on how to run it going forward over the subsea cable systems. Okay, first of all, just a really quick introduction. Who's Pacnet? In case some of you are not aware, we're a Pan-Asian telecom provider with extensive subsea assets. Those in particular, the EAC and C2C cable systems, and soon to come live Unity EAC Pacific cable system on Trans-Pacific. This is just a quick slide, just very general slide showing the broadband penetration rates in order in Asia, and all these eyeball traffics are mostly running on the subsea cable systems. Unlike other continents, Europe, US, in Asia, most of the traffic, we estimate up to 95% of the intra-Asia traffic is through subsea cable systems, and with the primary gateway being Japan. Now, there are cable systems from the US to Asia, not via Japan, but in most cases, it's most of the ring topology. The major cable systems do go through multiple landing station points in Japan. As mentioned, most of the IP traffic is via subsea cable systems. It's typically via a physical ring topology connecting all the different countries. Cable length is between 1,800 and 3,400, which is not. This is taking EAC as an example. This is not too great to be out of reach of certain technology like 40G. Or even greater in the near future. How are layer 3 point-to-point backbone circuits between the US and Asia connected now? You might have a point-to-point link from the US to any country in Asia, but the physical path is via a Japan cable landing station, just because of the fact that most of the cable systems connect through Japan. Large internet service providers in Asia, they have their main aggregation point in Tokyo. So on the layer 3 side, it's point-to-point from the US to Japan POP, 1 or 2 POPs in Japan, and then branch out from Japan and spread out to all the other countries in Asia. And C is a combination of both ISP that might have their main aggregation point in Japan, might have main aggregation in Tokyo and branch out to other countries, but they might have some tactical backbone direct to other POPs, US to Asia as well. The main point being in this slide is that basically physically everything, mostly everything goes through Japan cable landing stations. Okay, just jump around a bit now. Now, I guess you can see the importance of the subsea cable system now in Asia. Now, basically most of the traffic, internet traffic, is riding over them. So for those that might be aware of how the subsea operations work as far as cable faults and how they're taken care of in the time frames that we're talking about when there's outages, just go through, jump around a bit and go through that section. These are subsea SDH ring protection mechanisms being used by the cable systems in Asia right now, the predominant one being the last one, MS Spring. Basically with this, you can see in this ring protection, normal condition, for example, traffic would go through these 3 nodes as pointed out here. But then when there's a cable cut, it's rerouted. And there's something called the TOP, Transoceanic Protocol. What this does, it adds a little bit of intelligence at the SDH node layer, whereas, use my laser pointer here. Normally with MS Spring, what it would do is if there's a cable cut, it will reroute basically to the node on the other side where the cut is, and it'll ping pong back to its original path. But with Transoceanic Protocol, it adds a little bit more intelligence that it knows to reroute around paths that aren't related to the overall end-to-end circuit. So this is pretty significant on subsea systems. These legs right here can be several thousands of kilometers. So this helps to reroute things a bit more efficiently on the subsea SDH side. And this is the power feeding of the cable under normal conditions. So why do we need power going along the cable? Well, we have in 50 to 75 kilometer increments, we have repeaters on these subsea systems. And on one side, there's a PFE feeding positive voltage. On the other side, there's a PFE feeding negative voltage. And it maintains a constant current with the earth on both sides. And you can see in the middle, there's a virtual earth. So there's an equal amount of positive and an equal amount of negative voltage coming on both sides. So this is a normal condition. In a fault condition, for example, a shunt fault or something where there's an issue or leak for power where there's a cut or something, that virtual earth now becomes a physical actual earth. So this station will send current to compensate and maintain a constant current, and this station will do the same from the other side to maintain a constant current up to the physical earth. And in this case, if it's what they call a shunt fault, if it's something just with the power sheathing around the actual cable itself, and it doesn't affect the optical, the core fibers, then it's possible to maintain service over this subsea cable just by this compensation onto that fault, and they'll keep it in that state as much as they can until they can go out and actually repair it. This one just diagrams, you can just visually that you have on the same physical cable, you have the optical cores and you have the copper conducting material around it for the power. And when there's a shunt fault, they can take voltage measurements to guesstimate where the shunt fault is. If there's 2 shunt faults in the middle, then that basically takes out the service. But what if there's an actual physical cut? If the actual cable is broken up to the point of the fiber as well, well, that basically stops service. But how do they find the point of break? Well, there's optical measurements that can be taken too. The station will send a test signal through the repeaters, and the repeater amps will return the signal. So each repeater can return the signal, and when it gets to a point where it doesn't reach the next repeater, the repeater before the break will actually can detect the refractive signal off the actual cut. So the light will actually bounce off the actual part of where the cut is. And then the repeater amp that it comes back to realizes that it knows that it shouldn't get a signal back. So when it does, it knows that's related to a cut, and it'll reroute it back to the station. And then with the sensitivity of the test equipment, they can detect via the latency the distance within 20-30 meters of the actual break. And this is just a signal analyzer, a layer 1 subsea analyzer, and you can see normal conditions of test signal. Over a distance, the loss will go down, but when it hits a repeater, it'll bounce back up. So you just get this kind of formation. It might not be always be in an upwards pattern. It might be in a downwards pattern, a straight pattern. This happens to be a real actual output of a cut. This one happened to be in this kind of pattern, and then when it gets to the point where the actual cut is, then you can see, nonsense where the cut is, and that's where they estimate where the cut actually is. So they can now take a ship out and go out and fix it. Okay, here I got some nice drawings for you. Sorry I couldn't animate it. These are from our Subsea guys. Okay, basically they can locate the fault. So what they do is they do a cutting drive. They have to cut the cable so they can pull it up and repair it. And they'll hook the cable. Actually, in this picture you don't see the dimension, but this actual cable where they hook it, this distance from where they hook it to where they cut it is actually longer than the depth of where that cut is. So if it's a 5,000 meter depth, this might be where they grapple it might be 10 kilometers or so where they grapple it, because they have to have some slack on it, because when they pull it up they don't want it to fall off. And they'll pull it up not directly straight up. They'll go along the cable path as they pull it gracefully. And when they get it up, they cut the portion where they grapple it and tie it to a buoy, and they go do the same thing on the other side of the cable. Basically, similarly, leave some slack on it, pull it up, and they put a tie box on it, and they run new cable from that new splice all the way up to where the buoy is, and they'll tie it together, and they'll drop it down. And it actually does look like this when they do a repair. It's a V-shaped where they repair the cable. So there's a little bit of added distance, but it's not significant added distance where it affects the distance between the repeaters. The repeaters can compensate if there's a little bit of added distance, 10 kilometers or so. And they have to drop it perpendicular, because if they just drop it like that, the cable will tangle and twist and break again. So they have to gracefully lay it perpendicular to the actual original cable path. And each one of these slides, you can estimate about a day's worth of work. So if there is a cable cut affecting service, depending on weather conditions, where the cable ship is as related to where the cut is, it might take a week or so just to get to the site, and then all these slides are about a day each, so about another week to do the final repair. So you can look up to 2 weeks worth of outage in some cases. So during that time, traffic will be routed. If it's a ring architecture, be routed on a different path, maybe with longer latency, and it can have an impact to customers. Okay, we go back to the IP backbone design in Asia. What are some of the challenges? Well, not every country is the same. The volume as well as the inbound-outbound ratios are quite different among all the different countries. So it's tough to make a proper design. It's not easy to change the aggregation point. Basically, what that means, like everything layer 3 wise, most of it goes through Japan. It's not like Trans-Pacific feeding Asia, where on the West Coast you have LA, you have the Bay Area, you have Seattle. You can basically get the same amount of gravity, the same amount of transit through those locations. But in Japan, it's basically Japan is your main aggregation point. Low statistical multiplexing, basically just the fact that customers are reaching the speeds of the max bandwidth that we can have on the cable systems now. This is just the illustration of what I mentioned. Just at Korea, for example, there's more outbound than there is inbound from the Korea's perspective, and other countries in Asia are opposite, pretty opposite. Okay, this is the traditional Asia-US backbone architecture now. Basically, on the bottom is your subsea cable system going along different cable landing stations. It's kind of a fishbone type of architecture because each country has to have backhaul to the POP. So you have, from the US, you have your backhaul to the cable station on the West Coast, and then you have your Trans-Pacific link. And in Japan, you have your backhaul to the Tokyo POP. And excuse me. Basically, if you look at, maybe it's kind of hard to see on the diagram, but if you look at the red line here, that illustrates the design where Tokyo is the aggregation point. So traffic, transit traffic to Hong Kong, for example, if Japan is the main layer 3 aggregation point, it would come into the cable stations in Japan, ping pong to the Japan POP, and then ping pong back at the back to the cable station, and then on to its destination. So you can see one of the main things that's not efficient right now is this ping ponging on the backhaul, especially in Tokyo. So you actually, if a lot of the traffic for other countries is U.S. transit, you basically have to care for that on this backhaul path, and sometimes you can have up to double of the capacity that you really need on this path. And one other example is if you had a circuit U.S. all the way to Hong Kong, the path it would take is like this. It'll go through the cable station, hit the SDH equipment, the SDH equipment protection ring, go all the way to Hong Kong. This isn't efficient as well because that particular path, that particular circuit that traffic is running on is only going to be used for Hong Kong. So we want to look at what are some of the things that we can do a little bit better. One of the ideas is putting a router at the cable station, doing your IP routing and your switching, adding the intelligence, a new layer of intelligence closer to the actual, subsea cable system itself. So if you had assets, cable station assets, if you had the subsea cable system itself, you might have an opportunity to build out something like this. So now, U.S. transit traffic bound for Asian-bound countries, it'll come into the subsea or the cable stations, and instead of going to the SDH equipment, now the router replaces the SDH function. So it'll go to the router, and then if it's bound for Tokyo, it'll go over the backhaul. If it's bound for other countries, it'll go onto the next cable station, to the next router, etc. So this will allow for better utilization and better management of the capacity. Now, it's not just Japan that has this ping-ponging. There's other countries that may transit other Asian countries as well. Singapore might transit Hong Kong, etc. So there's some efficiency we can gain by putting a router at the cable station. Okay, basically this is just a simple diagram showing here's the traffic pattern, and then now we have, since we're taking out the SDH layer, we have to have some mechanism to maintain the fast switching that SDH gives us, which is in the 50 millisecond ranges. So we want to take advantage of all the cables, or all the subsea segments that we have connected, and create protection paths, maybe using fast reroute. So we can create protection paths using different cable systems, DAC or C2C. And what's the design concept? There's no longer a traditional ring protection mechanism on top of the subsea, and then layer 3 on top of that. We want to use 10G WAN-Fi because WAN-Fi can detect similar alarms and errors that SDH interfaces can. The MPLS LSR, the router that we're going to install in the cable station, that LSR can perform a fast reroute, and it can take the place of the ring protection that the SDH gave us. So the subsea is basically 1 + 1. You have reserve, standby, unusable capacity, whereas this you would have active and standby LSPs. So it's a reasonable replacement for SDH. And depending on what kind of mesh that we want to make this new network, as far as MPLS, we can use the do traffic monitoring and capacity management using the LSP traffic data. Add additional route reflector hierarchy. Basically, a lot of networks in Asia, they're using per country route reflectors. So some cable stations might serve more than one country. So we might be able to make the cable stations, if we want to participate in BGP, make them route reflectors of route reflectors, or something else. It's just another thing we can consider as far as how we want to do BGP with these new routers at the cable station. Last point there, there's no GAMPLS ASON type of design. There's no C plane, D plane separation in this network. It's all flat. And what are some of the network advantages? In one point for Japan, for example, if the aggregation point is Tokyo, everything goes through Tokyo nodes. We can bypass that if there's a major disaster, an earthquake or something that takes it out. It won't affect other Asian POPs, as long as the earthquake doesn't affect the cable station. There's route. Hello? Okay, sorry. There's route flexibility. We can use explicit LSPs to utilize the protection path that SDH wouldn't allow us to use. We can do better tracker aggregation at the cable stations, and by we can eliminate the SDH hierarchy and aggregate on the LSP level and use flexible bandwidth. Also, as long as the SLTEs, the subsea line terminating equipment can be upgraded, our router's already at 40G up to 100G now. So as long as the SLTEs can support it, we have an easy path to upgrade it to a higher capacity in the near future. We don't have to worry about the SDH layer, and without the SDH layer, we can save. Goes without saying we can save significant capex. And what are some of the things that we need to do to prepare? We need a high-performance router at the cable stations. We don't want to do any virtual router function on those boxes. We want them to have physical redundancy. Use single interfaces as much as possible. That helps with sparing and troubleshooting and quick provisioning. And of course, we want to have IPv6 enabled. Depending on how we design the network, then we can consider how we want to deploy IPv6 over it. Okay, that was jumping around a little bit. With this subsea architecture with high capacity, what are some interesting things that we can do at the layer 3, layer 2 level? One idea is as an Asia regional IX. I don't believe there's any regional IX or virtual IX throughout the region in Asia today. Today in Asia, we have commercial IXs operated by telecoms. We have data center IXs. We have nonprofit IXs operated by educational as well. So, and then there's layer 2 IXs and there's MPLS IXs, but a lot of the main well-known IXs in Asia are still at the layer 3 IXs using route servers to advertise and receive routes to their members. So it's not as predominant in other continents, but it's still in Asia. Do we need this regional IX? Well, yeah, it'll allow us to provide large switching between traffic exchange between peering members. What are some of the initial design concepts? We don't want to do a layer 3 IX initially, just a simple layer 2 IX. Use MPLS as a transport, maybe with a VPLS solution. And then you can have peering can be done POP to POP. So a member, these can be POPs in different countries. So a member in Japan can peer with a member in Hong Kong, for example, if they're connected to this IX in each country via colo or local loop. What other ideas can we think about for this regional IX? Well, we can consider this being an IX of IXs. We can consider bridging two IX exchange points. There might be a lot of issues with that, security issues, etc. But there may be IXs that are interested in this, especially since, some IXs in Asia they're pretty static now. They want to attract more customers, whereas an outlet to do that, maybe this might be a solution. Depending on how open we want to make this regional IX, we can transit can be offered between members over this infrastructure as well. And also with this IX, regional IX, with a single connection by the member, it allows us, if it's a trunk connection, allows us to provide peering service as well as selling our own transit service or offer any other additional service as well. And if with the different Ethernet exchange points that are coming up and popular now, if we can interconnect with Ethernet exchange points, it'll allow us to extend the reach of this regional IX even further, possibly. So also, if anyone else has any ideas regarding the regional IX and what it might mean for you, feel free to provide any ideas. Very
seems to have a sound problem.
Yeah. Hello? Okay. Maybe it's me. I'm not doing this right or something. I don't know. But it's very high-level diagram showing the IX, and you can see from here, this is an ISP in one country, another ISP. They can peer with each other over this regional IX. Or if, like the bridging method that I talked about, there might be a member that's connecting to this regional IX, and they want to peer over a member that's connected to another IX. Or in this third example, ISP connecting to IX in both countries want to peer over or peer to each other that way. Or the Ethernet exchange method that I mentioned, ISP wants to peer with a member that's connected to an Ethernet exchange. So it offers a more additional access methods using the exchange. Okay. Well, that's about it for me. I went through it pretty fast. I hope I didn't jump around too much. But we're on time? Okay. Thanks again for your time. If any questions, feel free to contact me. Thanks.
Thank you very much.